So we continue, guys. You want to add something else? So we can discuss other symptoms of hypoglycemia or insulin overdose. Maybe something like, I don't know, dizziness, lightheadedness. Guys, keep them coming. Okay, palpitations, hypokalemia, tremors. Okay, then how do you manage hypoglycemia? Okay, I'm saying in the group, other, what have we, irritability, restlessness, excessive hunger. Yeah. There's also a mnemonic there to remember some of those signs. He's tired. Okay. There says for hypoglycemia or insulin overdose, you give what glucagon and dextrose, but he's not sure. Someone else tell us. Most patients are told to take chocolates, or you can take those glucose tablets or some sugar that is before you get to hospital, or something to boost that. Yeah. Anything else, guys, we need to discuss? There's also an image that has been sent on the group showing the causes, symptoms, and even how to manage hypoglycemia. So I think we can move on. Okay. Yeah. Then the next question, proton pump inhibitors may cause increased production of HCl, are known to cause severe hepatitis, do not cause nephritis, or are not associated with angioedema. Which of these effects is true about PPIs? Okay, I'm seeing someone has also added in the group for hypoglycemia, we give the 50% dextrose. Okay, right. Uh-huh. Someone was saying something. Okay, then maybe we can just, I don't know. Proton pump inhibitors, they may cause increased production of HCl. Proton pump inhibitors, they actually do the reverse of that. So not that. So definitely not A. Then B, they are known to cause severe hepatitis. I have no idea if they cause then hepatitis. So you're sure you guys can help with that. Do they? Okay, I'm not sure. Then C says they do not cause nephritis. Actually, PPIs are associated have there's a relationship between taking PPIs and acute nephritis. And then they are not associated with angioedema. Guys, help me with, okay. Hiral says B, they are known to cause severe hepatitis. Okay. So what are the other side effects of PPIs now that, okay, Hiral tells us they cause severe hepatitis. They also cause nephritis. What are the other, okay. So on the chart, I'm saying they are associated with hepatitis, cholestasis. Okay, okay. Oh, they are all types of hepatitis, okay. They're also associated with vitamin B12 deficiency, fractures. Also, I think B6 yeah, no, vitamin C deficiency. They increase the risks of infection, porosis, yeah, and so many others. Then for cardiac, they may cause cardiac infarction, heart rates, heart failure, and such. Yeah, enteric and respiratory tract infections. I think something has been sent in the group. Yeah, for the other side effects of PPIs.
Also, as we mentioned about,
Also,
as you mentioned about before, like if you stop PPIs immediately, they will cause severe rebound acid secretion. So that's a side effect of withdrawal from PPIs if you stop. So you're supposed to tap the drug or the dose.
okay. So we can continue. Which one of the following is a weak acid? Which of these is a weak acid? Hydrogen chloride, hydrogen bromide. Have I said hydrogen chloride? Anyway, yeah. So which of this is a weak acid? Okay, I'm seeing for in the chat box, keyboard warriors wanasema choice C. So for what do we call for hydrogen halides, how does acidity change down the group? Or yeah, something like that.
Okay, so for acid strength, it increases down the group because the size of X, so that's like either chlorine or bromine, increases. So the bond between hydrogen and that other molecule would it weakens, so that increases acid strength. And even across the period, acid strength increases because of electronegativity and polarity increase. So I guess C would be the answer.
It's either a period or down the period.
See,
There's
you
that
said
limit.
acidity increases across the group.
Yes, and even across the period. Down the group, it increases. Across the period, it also increases.
Okay.
Okay, are we good there? Okay, moving on. All of the following are weak bases except
D.
okay. Someone says B, and then we've talked about the acid strength for the previous question where we've said it increases both across the periods and down the group. And then someone is also asking, how about the base strength? How does it change either up or down the group?
Base strength is now the opposite of acid strength. So down the group, it decreases, and across the period, it also decreases.
Okay, Nugal, is that okay?
Yeah.
Okay. Okay, and then we continue now. So all the following are weak bases except magnesium hydroxide. Do we need to discuss anything there, guys?
I have a question. Isn't hydroxide a strong base?
Yes.
So why hydroxide is usually a strong base, right?
Yes.
Then why is it? Oh, okay, sorry. Weak base, except. Okay.
Okay. Okay, then we continue. So which of the following statements is false concerning equilibrium? So equilibrium shifts to the left when a component on the left is removed, or does equilibrium shift to the left if a reactant is removed, or does equilibrium shift to the left if a product is added, or does equilibrium shift to the left if a reactant is added? So how does the concentration of reactants and products affect equilibrium?
According to Le Chatelier's principle, a system in equilibrium wants to remain in equilibrium. So if we increase the reactants, more product will be formed. If we increase the products, more reactants will be formed. The system will shift to utilize that change. Yeah.
Wait. So by your explanation, the answer will be
D.
D.
Dog.
Isn't that to the right?
See, the reactants are on the left side. So if you've increased reactants, it means equilibrium will shift to the right to favor formation of the products.
Oh, it's false. Sorry, I read what is right.
Yeah.
Sorry.
Anything else for that question we need to discuss?
I think maybe we can remind ourselves about the principle, the Le Chatelier's principle.
So the principle normally states that when a change in concentration, pressure, or temperature is applied to a system at equilibrium, the position of the equilibrium will shift to either direction that tends to reduce the effect of that change. Okay, I don't know. Someone can send it in the group, maybe, so that we also discuss the effect of now those other factors like temperature and pressure on the system. Okay. So something has been sent in the group where we have a reaction at equilibrium. So if you increase, like Gaz has said, if you increase the concentration of the reactants, you will favor formation of more products. If you increase the concentration of products, then you will favor the backward reactions. And then If you, now depending on if the reaction is endothermic or exothermic, if you increase the temperature, it will definitely favor the endothermic. If you increase the pressure. What am I saying? If you increase the temperature, you favor the endothermic reaction. And then if you increase the pressure, you will favor the reaction in the side that has fewer molecules.
For temperature, just remember that if it's an endothermic reaction, then heat is a reactant, while for exothermic, heat is a product. So if you increase, for example, if the reaction is endothermic and heat is as a reactant, if you increase the temperature, then you'll get more products, and vice versa for exothermic.
Okay, thank you for that, Hirar. Okay, there's something in the chat box that I'm not understanding. Someone help me understand that, please.
I think that one is about the calculation, the initial, the change, then the equilibrium. Exit. Equilibrium. Yeah. You say initially it was this, it changed by this, then it went to this. There was that there was a way we were calculating. Maybe let me look for a photo and send.
Yeah, that's okay. You look for a photo. If not, I'll find one after the discussion. Alafu nikielewa nitawaelezea 8 p.m.
Perfect.
Okay, so we can continue. Okay, which of the following statements is false concerning the effects of changes in pressure on equilibrium system with gaseous components? So which one is false concerning the effect of changes in pressure on equilibrium system with gaseous components?
Will it be B? Because I'm assuming because the gas is inert, it's not gonna take part in any reaction.
Okay. Okay. Yeah. So yeah, like we've said in the previous question, when you increase the pressure, it favors the side that has less, what is it called? That has less molecules. So then of course we know with pressure, when you increase the pressure, the volume definitely decreases, and then you can now at least use that relationship to see, like in C, when you change a reaction vessel, volume affects equilibrium. So when you change the size of the vessel, the pressure will either decrease or increase, and that will definitely affect equilibrium. And yeah.
So what's the explanation about choice B? Like adding an inert gas affects the equilibrium position. That's not true. Like inert gases, they won't do anything in terms of pressure or like what's the explanation? How is the statement wrong? That's my question.
Or ordinary natural gas affects the equilibrium position. Okay, I think from just the straightforward looking at it, may just assume adding an inert gas doesn't react. But then now with the pressure, if you add an inert gas, definitely the pressure changes.
Yeah, because I was thinking the same. And if the pressure changes, it may affect the equilibrium. Like that was my thinking. Then what about choice D? Changing pressure by changing volume often causes a large change in equilibrium position. Is it usually a large change? Like I agree it causes a change, but is it usually large?
Okay, maybe we can just check that, all of us.
Somebody has put on the group that when you add an inert gas, it will increase the total pressure of the system, but it will have no effect on the equilibrium condition. So that makes B the right answer.
Okay, thanks.
Oh, so okay. So that means okay, there will be no net effect in the equilibrium condition. Okay, it's okay. I was just trying to understand that. Okay, we can continue if you guys are okay. Okay, the physical properties that depend primarily on the sum of the properties of the individual atoms forming the molecules are generally classified as. Okay, I'm seeing someone is saying additive properties. Okay. Then Hiral is asking about the other choices. Okay, we can actually discuss all the choices. Okay. So we start with which one? Colligative properties. I think we discussed colligative properties. Okay, someone says B is the answer, colligative properties. Okay, now I think we can just basically explain each of them, then we can figure out which one is the right one. So you can just explain whichever term you want to explain, either on the chat box, in the group, or you can just unmute. Yes? I hear
On the
someone.
previous, so it's not on this question. On the previous question, which answer did we go with? Okay.
So I'm searching here. Colligative properties are the physical changes that result from adding a solute to a solvent. Colligative properties depend on how many solute particles are present as well as the solvent amount, but they don't depend on the type of solute particles.
Okay, then while you're reading that, you can also give us some examples of colligative properties.
Let me check. So there are 4 of them: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure.
Okay, so those are the 4 colligative properties, and they don't depend on the individual
Types.
but just the overall, okay?
Yeah.
And
The
are there
physical change
on the
result from
textbook?
adding a solute to a solvent. Haya. Stanley ametuma kwa group. Hebu tukaangalia kwenye ametuma.
Okay, Stanley ametuma colligative properties, which you have just explained. Then I'm seeing Fatma has sent something else on additive properties. Those are properties of a substance which depend on the sum of corresponding properties of the constituents, and those are now the additive ones, like the mass and the molecular weight. Then, Tracy is constitutive properties. These are properties which are mainly dependent on the arrangements of constituents and to a smaller extent on their number and natures. So then from that explanation, I think it's maybe additive properties, because that's the property of a substance which depend on the sum of corresponding properties. Okay, then someone please help us check for us what intensive properties are. I'm reading somewhere about intensive properties, and it says that there are properties that are independent of the amount of substance present in a sample. And this kind of properties exist at molecular levels and are inherent to the chemical composition.
Then the opposite of intensive I'm seeing is extensive. It says the properties that are dependent on the amount of substance present in a material sample. And these include weight, length, volume, entropy. I will send to the group.
And then also we can discuss about each of those colligative properties. We said there are 4 of them. Now we can discuss at least each of them individually. Okay. My guys, sioni mkinipea
It's in the
information about
notes.
each of
I can
those.
send it's in the notes. I can send the PDF, but someone who is good in this chemistry stuff can explain and summarize what. Yeah, so let me send the PDF to the group.
Okay, guys, there's that PDF that Fatma, she sent the PDF in the group. Maybe we can just discuss them.
Okay. So we've seen the definition of colligative properties. That's it depends on the concentration of the solute molecules or ions in solution, but not the chemical identity. So it's either by vapor pressure, boiling point elevation, freezing point lowering, and osmotic pressure. So when we talk about the vapor pressure lowering, it's the partial pressure of the vapor of a solution and the pure solvent. So it says that the partial pressure of solution should be less than the vapor pressure of the pure solvent. So if the solute is non-volatile, then the pressure of a solution is mole fraction of the solvent times the vapor pressure. That's the Raoult's law. So I think when we were doing in the starting, like the first week of this inorganic chem, I think we had seen one of the questions which was talking about Raoult's law, and you need to remember that it's vapor pressure of the pure solvent multiplied by the mole fraction in the solution. Yeah, so when a solute is present, less of the surface is occupied by these solvent molecules. Does that make sense?
Yeah, it does.
Yeah.
Yes.
Okay. So remember that the solution is always less than the solvent. Then we've seen how to calculate the partial pressure for solution. Then boiling point elevation. Okay, the boiling point elevation is a colligative property So here we need to know the formula as well, which states that the molar concentration multiplied by the boiling point elevation constant. But I don't know how this boiling point elevation works. Maybe somebody can expand on that one and the freezing point. Those two are a bit confusing.
Shrina, can you hear me?
Yeah.
Now for the boiling point and freezing point, I found it easier just relate it as you said. It's a solvent, then to which a solute has been added. It's like a solvent with an impurity. So the way we say, when you put water, when you put salt in water, it will raise the boiling point, but it will lower the freezing point and the melting point. So I find it easier to relate it to that, in that when solvent molecules are just there, the boiling point will be 100 degrees Celsius. But when you add solute molecules to the solvent, there'll be a raise in the boiling point. Yeah. I don't know if that simplifies it.
Yeah, it does. Okay. Here, should I repeat for the vapor pressure?
Yes, please.
So, vapor pressure is basically the partial pressure of the vapor over the liquid. Yeah. So you need to know that when so the vapor pressure of a volatile, if the solvent is volatile, it's the vapor pressure will reduce if you add a pure solvent in it. That's in simple terms. If you add a pure solvent to a volatile solvent, then the vapor pressure will reduce.
So basically an impurity reduces vapor pressure. Or?
No, a purity reduces. If you add something that is pure, it will reduce the vapor pressure of the volatile solvent.
Okay. Thanks.
It makes sense.
Yeah. Thanks.
Yeah. Then what is left? The osmotic. Osmotic pressure is just like the way the name goes. The solvent is going to pass through a semi-permeable membrane, and the solution is going to, concentration is going to equal on both the sides. So for that, the formula is just molarity times the room temperature times the gas constant times temperature. Molarity multiplied by the gas constant. In this gas constant, you are using 0.08206 and multiplying it with temperature. Yeah. That's it. Yeah, and Fatima has shared the summary for the formulas, so it's going to be there. Thank you.
Okay, thank you, guys. And then now we can continue to the next question. Which of the following solutions will form an ideal solution when mixed together? So which will form an ideal solution when mixed together? So first, what are ideal solutions?
Google says an ideal solution is a mixture in which the molecules of different species are distinguishable. However, unlike the ideal gas, the molecules in ideal solution exert force on one another. So they are distinguishable and exert force on one another. Examples are chlorobenzene, bromobenzene, methanol, ethanol, and an ideal solution include kerosene, acetone, sugar solution.
Yeah, so she's explained to us what ideal solutions are, and she said irrespective of the molecules, they exert pressure on one another. So if the forces each of those molecules is exerting on the other is the same, then the solution is ideal. So like if there is no, let's say there's no net, there's no one that has more force than the other, then we'd call that an ideal solution.
So a simpler way to remember how to make an ideal solution is by mixing the solute and a solvent which has the similar molecule structure and size. So methanol and ethanol have a similar structure. So I think that's the best for an ideal solution when mixed together.
Okay. Then in an ideal solution, the partial vapor pressures of each volatile constituent is equal to the vapor pressure of the pure constituent multiplied by its mole fraction in the solution. So this relationship is referred to as, I think we've just discussed that right now when we were discussing the colligative properties. Okay, Raoul's law.
Yeah, it is. Can somebody talk about the Dalton's law?
Dalton's law is just the total pressure of, like, if you have many gases, so just the sum of all their partial pressures.
Okay, I'm seeing in the chat box, it has also been written, the equation has also been written. It's the sum, yeah. The sum of the partial pressures. Okay, 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 Hiral has also typed the law in the group. Okay, do you need to go through the other laws? Sure, I think we can continue. Okay, all of the following compounds are cationic surfactants, except which one? So which one is not a cationic surfactant? Okay. We're on question 114. Something on the chat box, they've said chlorohexidine. What are the types of surfactants? Have we covered this before, Shrina?
We have covered it, but I don't know if how to remember them. I get confused personally, so I don't know how to remember these different types. I only know the headings, but I don't know the examples of it. So I don't know how to remember them.
Who has an easier way of remembering the surfactant? Anyone? Chlorhexidine is a cationic surfactant. I can see cetrimide is cationic, definitely, and also benzalkonium. So I don't know what about benzethonium. Anyone who knows that?
I think all the quarks are cationic surfactants.
Okay. Anyone else with a different opinion? I can see there's a document that has been sent by Dr. Tool. So what answer would you go with here? Because I think all of them are cationic surfactants. Should we just put a star or if anyone finds anything, I think you'll just let us know. So for question 115, which one of the following interfaces is of least pharmaceutical significance? So choice A, gas liquid, liquid liquid, solid liquid, or solid solid. We have Dr. Hiral saying choice D. I also think choice D. Anyone else? Any other opinion? Some is saying choice C, solid liquid. Some kindly. Some is it for 114 or 115? If it's 115 or 114, either way, kindly feel free to unmute.
Before I like, do you guys have a valid source for D?
Sorry?
Hello. Do you
Yeah, we
guys have a
can.
valid source for D before I share my other source? AI and
Okay, let's hear yours first, and then I think Dr. Gaius will explain why choice B.
sorry. I actually agree. Choice D is actually the correct answer. So
Oh, okay. I think we're all in agreement.
But can the answer be explained?
Yeah, let me see. We can have Hiral or Gaius or Dash, or me, one of you can unmute and explain. Gaius is suggesting some to explain.
okay. Okay, so they're asking should the following interfaces is of least pharmaceutical significance. So for gas liquid interfaces, in my opinion, I feel like they're very significant because they're basically what you use for dispersing some gases or liquids in gases. Okay, some aerosol sprays, I'm thinking. For liquid in liquid, of course, we have very so many solvents that are mixed together. For solid in liquids, we also have lots of suspensions which we have in the market. So solid in solid, okay, I feel like they're significant, but okay, to the degree of all others considered, I feel like they're of the least significant in as much as they are significant. Okay, that is just my opinion. I don't know what someone else has to say about it.
Thank you, Sam. Anyone else with different explanation or an opinion or a different opinion? Anyone? Oh, I think, okay. If there's no other contribution, I think we can move to the next question. On the chat, I've seen something sent by Dr. Mbuvi. You can kindly share to the group so that everyone can access also, for those who are not here. For question 116, a surfactant which when dissolved in water lowers the advancing contact angle and aids in displacing an air phase at the surface and replacing it with a liquid phase is referred specifically as a wetting agent, choice B, a deflocculating agent, C, an emulsifying agent, and D, a suspending agent. So Dash is saying wetting agent. I also agree with that. Him or her. I think Dash, you can explain to us why I think A. Is it blank?
Yeah, I think generally the term a wetting agent, we describe it as it would be that substance that lowers the contact angle. So just based on that alone, lowering of the contact angle, then it would just be a wetting agent.
So what are some of the examples of wetting agents? My keyboard warriors, munalala.
Wetting agents are surfactants which we discussed earlier on. The different classes of surfactants.
Yeah. Oh, we have SLS, sodium laurate, sulfate, yeah. Such like quaternary ammonia compounds. Yeah. Shrina, I guess. Yeah, we can move. Which one of the following rate equations represent a zero order reaction where A sub O means initial concentration of reactants, A concentration of reactants, time and K rate. I think we've sung this over and over and over and over. Yeah. Unless anyone has a problem, the answer is C. Anyone with a problem, or we can move? I think we've covered rates of reactions. Yeah, can see Shrina is highlighting choice B. Choice B is first order, choice D is second order, and C is 0. Okay, so for question 138, which one of the following drugs cannot be taken orally on account of incompatibility with the gastric acid? I think we covered this question before. And we went with benzyl penicillin. What is the basis for incompatibility of aminophenyl and benzyl penicillin co-administration as an infusion? Choice A, alkaline pH shift causing degradation of benzyl penicillin. Choice B, alkaline pH shifts causing degradation of aminophenol. Choice C, addition of aminophenol causes precipitation of benzyl penicillin. And choice D, chemical reaction between the two drugs. I think Dr. Stanley can take us through this one. He told me he knows the answers. can see Dr. Nugal saying choice A. Maybe you can explain it.
It's from Google. So it says aminophylline has an alkaline pH. So the alkaline pH now will cause the degradation of penicillin, benzyl penicillin, I mean. I think that's the simplest. Why it has an alkaline pH, I don't know, but that's what it says.
Aminophylline is a base.
Oh,
Pardon?
then that explains it. She said aminophylline is a base, so its alkaline pH will now degrade.
Okay.
Yeah, penicillin, benzyl penicillin.
Okay, so that makes choice A our answer. Unless anyone has a different opinion. Yes, me. Me saying choice C. Maybe you can kindly explain your answer. Because now we have choice. Some other people saying choice A.
So I'm thinking we've said aminophylline is a base. Okay, yeah, so it will be relatively stable in the alkaline pH. Secondly, we have seen from question 118, benzyl penicillin is unstable in acidic pH only. So that makes choice A and B are not be the best choices. Moving to choice D, chemical reaction between the two drugs, that's too general. Yes, making choice C to be the best answer. Also, from Google, I've seen that aminophylline, when aminophylline and benzyl penicillin are co-administered as a bolus, they cause precipitation, which may block the layer. So I will go with choice C.
Okay. Anyone else with a different opinion? But I still don't understand how it will form a precipitate. Because if aminophylline is what? Is a base. Okay. Wait.
Okay, I found something. Maybe I can share. Okay, I can read it, alafu I'll share it kidogo tu.
Okay.
So, okay, basically, what the previous person answered was C. I'm still getting the same answer. Okay, using an AI because it searched the web, apparently. So it's basically saying, this is, okay, addition of aminophylline causes precipitation of benzyl penicillin. And this is because aminophylline is a salt of theophylline and ethylene diamine, and benzyl penicillin is a salt of penicillin and sodium or potassium. So when these two salts are mixed together, they may form insoluble complexes that precipitate out of the solution. So however, this is, okay. Imesema, however, this is just its own opinion from the web search results. So you can make your own conclusion based on that, but I will share because there are also sources. Maybe I can just share it with you guys all of you to have a look.
I have a question. When penicillins, the benzyl penicillin is administered as an injection, it's given via IM, and we say the salts are the organic salts, not the sodium and potassium salts, if I'm not wrong.
Kindly repeat your question. I didn't get you clearly.
Oh, he was saying something that the penicillins are the salts of sodium and potassium. So I'm just asking, I'm saying when penicillin are administered as an IM injection, they're given as organic salt. The benzathine penicillin and procaine penicillin, if I'm not wrong, not as sodium or potassium salts.
From what I'm getting from the web, basically from drug bank, they're saying it's usually given as a sodium salt. So
So I think we can put a star and go with choice. Let's see. Yes. Unless Dr. Nugal is not convinced with the answer.
We can go on.
Yeah, so choice C. Choice C. For question 120, metal tubes used for packing salicylic ointments are lacquered to A. Prevent spillage of the ointment, prevent reaction between salicylic and the metal tube to prevent auto-oxidation of salicylic acid, and to enhance the durability of the packing. We have me saying choice B, the chat box. Yeah, I think me, you can. So lacquering, we know it's to coat it's like adding a coat. I'd also go with choice B, so it does not react to the metal tube, which will cause it to be unstable or degrade. For question 121, the reason for decreasing potency of tetracycline capsules during storage is degradation through A. Hydrolysis, B. Oxidation, E. Epimerization, and D. Tautomerization.
Can you please explain?
Question?
121.
Oh, I've not yet said an answer. Oh, choice. Oh, you have me saying C. Yeah, kindly explain.
Yeah.
Me, you can unmute and explain why choice C.
Yeah, so it's Tracy because the chemical degradations or the processes that affect tetracyclines majorly are gelation, epimerization, phototoxicity, and dehydration. So we don't have oxidation, we don't have hydrolysis, we don't have tautomerism. So I'll go with C.
I asked to please write them in the chat. You can send them in the group. Oh, there's another document that has been sent to the group by Dr. Noor.
Can I explain the reason why it's tautomerization?
Yeah, go ahead.
So the tetracycline undergo epimerization reaction to form an hydrotetracycline, which is non-toxic. Okay, which is toxic and inactive. So the reaction that is undergone is epimerization reaction.
And repeat again.
I said the tetracycline, they undergo epimerization reaction to form epi and hydrotetracyclines, which are toxic and inactive.
I'm seeing from what has been sent in the group, epimerization will only occur in tetracyclines under acidic conditions, but for here have been specified during storage. So
During
yeah.
storage, the reaction that are likely to occur.
Oh,
So
yeah.
whether those are the epimerizations, the reaction that is likely to occur to form the inactive complex of tetracycline.
Yeah, for this reason, tetracyclines should be prepared freshly and used to gain the desired maximum activity. So I think the answer is, yeah, we all agree, epimerization.
Lydia, had you mentioned something to do with tautomerism in your explanation? That's what I was asking.
Well, tetracycline undergoes tautomerism, like ketoenol tautomerism, at pH 6 to 7. So the enol form will be converted to the keto form, and the keto form is equipotent to the enol form.
So I think the answer is epimerization, right? Unless
Yeah, and then epimerization takes place at pH 2 to 6. Then there is dehydration that now takes place below pH 2.
Okay.
Yeah, if it's from tetracycline to epitetracycline at pH 2 to 6, then from epitetracycline to now the anhydrous from the epianhydrotetracycline that is now nephrotoxic, it's inactive at pH now less than 2. Yeah.
Thank you very much for that.
You're welcome.
I guess we are now all in agreement, so we can go to the next question. Which one of the following factors that influence degradation of the drug molecule is described by the Arrhenius equation? I think we did this question not long ago. So you can revisit the Arrhenius equation. For question 123, which one of the following drugs belong to the indole acetic acid class of anti-inflammatory agents? Choice A, indomethacin. Choice B, diclofenac. Choice C, ketorolac. And choice D, ketoprofen. I think this is almost direct. It is direct. The indole is indomethacin, unless we have any other opinions. Shina, we've gone through anti-inflammatory agents before, right?
Yeah, but I don't know if we did like Medicam classification, or maybe I'm wrong. I'm not sure.
I'm also not sure.
I know we did NSAIDs, but not like the Medicam classification.
So I've seen Dr. Bunaya has shared an image with the different groups and examples of drugs. I think we can go through that, the classes of NSAIDs and the examples. So I think in reference, one can go through that. So from that, I think our answer is indomethacin. And other examples are sulindac and etodolac. So for diclofenac,
Diclofenac is oral acetic acid.
yeah, I can see Dr. Sam saying the answer is in the name. I think the other examples are in the other classes of ketoprofen, diclofenac, and the image Stanley has sent. I think we can go to question 124. All the following properties of drug molecules are represented in the Hunt's equation for drug design except A, lipophilicity, B, steric effect, C, biological activity, and D, conjugation. So what's the Hunt's equation? That's been sent. So for the Hans equation, it involves drug transport and binding affinity, depending on non-linearly on lipophilicity. So from that, lipophilicity is there. Okay, let me check the formula.
The conjugation is not there. Maybe I can read the three factors.
Okay, go ahead.
We have, it usually includes the log P, which is the lipophilicity, the electronic and steric factors.
Pardon? For steric factor.
So the equation includes the, okay, let me just read everything. The quantitative structure activity relationship equation relating various physicochemical properties to the biological activity of a series of drugs. So usually it includes the log P, which is the lipophilicity, the electronic and steric factors. So the correct answer is conjugation.
Yeah, and because it is dependent on the drug transport and binding affinity is dependent not linearly on the lipophilicity that explains the biological activity. So conjugation would be our answer.
Can you please share that answer on the group?
Okay, the equation will be sent. For question 125, which one of the following antidiabetic agents is not correctly matched with its chemical class? We have, we already have someone in the chat box. Yeah, the answer is C. I think we've covered antidiabetics before, if I'm not wrong. Right?
I have a question.
Yeah.
But guanites and guanites are different, right?
Yeah, I am thinking. Let me just confirm. Or anyone? Difference between guanides and biguanides. And
What is the question again?
I can't hear you, you're breaking.
If you can repeat the question.
I was asking, someone had asked, is there a difference between guanides and biguanides?
I think the difference is when you say biguanide, it's actually two guanides combined together. So you have two structures of them.
I hope you've been answered. Yeah, I think the structure of guanide is like an N connected to a carbon bond. Yeah. I'll send the structure to the group. Yeah, it's what she's explained. Guanide one. Oh, I'm seeing mistake is saying guanides are cholinergic agonists. Thank you for that. So for question 126, dash is orally active anticoagulant that selectively inhibits factor 10A, indraparin. What's this? Email cancelled. Can't see clearly. In the Parindex, we have dabigatran, rivaroxaban, and I can see from the chat box, we have dash saying the answer is C. Yeah, we have Dr. Abdul Malik saying the easy way to remember is that 10A is in the same name of drug. Yeah, the XA, sorry, the factor XA, like the XA is also in rivaroxaban, and there's also a diagram that has been sent by Dr. Shrina. So when you see XA in the name, most likely it is an inhibiting factor. 10A. So our answer is C. Thank you so much for that. I think we can do these two questions and then we will meet at 8. So dash is commonly used for diazotization titration. So we have the 0.1 molar disodium ethicate, 0.1 normality of sodium hydroxide, 0.1 normality alcoholic acid, and 0.1 normality of sodium nitrite. So diazotization is used in the analysis of aromatic compounds containing an amino group in the molecule. So which one is commonly used? You can see, oh, there's no one that's typed. So I'm thinking the answer is sodium nitrate, which is primarily used. So So sodium nitrite is commonly used to react with primary amines to form a diazonium salt. So our answer is D, unless anyone is of a different opinion.
We discussed the different types of titrations.
I don't know, I'm not sure. Did we? So what are the different types of titration?
We have acid-base titrations, complexometric titrations, redox titration, and precipitation titrations.
Yeah, so we have the four. For the acid-base titration, an acid or a base titrant reacts with the analyte that is a base or an acid. For the complexometrics, it involves metal-ligand complexation reactions. For the precipitation titration, a titrant reacts to form a precipitate. And for the redox reaction is the one where we have the oxidizing and the reducing agent. Is there any other addition?
So where does this diazotonium titration fall under?
Um, I'm not sure where it goes under, but in the when you were doing the organic, I'm not quite sure where it falls under. Anyone? I think we can revisit that. We'll research and then we'll come back
think
to it.
under
Yeah, go
acid,
ahead.
I
Sorry?
think it is acid base. Have you gotten?
You said acid base.
Yeah, I said I think still under that. Because there's a place I read. Let me read it out. The diazotization titration is nothing but the conversion of the primary aromatic amines to diazonium compounds. This process was first discovered in 1853 and was applied to the synthetic dye industry. The reaction mechanism was first proposed by Peter, In this method, the primary aromatic amine is reacted with sodium nitrate in acid medium to form a diazonium salt. So acid and salt, maybe that's why I thought it is falling under acid base.
So you said now is the base the primary amide or which one is the base and which one is the acid? Kindly.
Niko world yangu ama hiyo acid and salt ni different.
I'm saying according to its equation, it's like you add an acid to make it like an acidic environment such as HCl. So I don't wanna help.
Okay. Also, the introduced acid will react with the
Like
the amide group. Now it will act as an acid base, right? No.
Yeah.
I think
No, in the reaction, you first react the HCl with the sodium nitrite, which forms the nitrous acid, which later reacts with your primary aromatic amino acid to form the yes, the diazonium salt. So I think she's writing with the acid-base reaction.
Yeah, okay. No, I've understood. Thank you. So our last question, Dr. Tur already gave us our answers. I think Hiral had covered this before. Bupivacaine belongs to the amide group.
Yeah, to remember if it's in the class of amide, you just see if there's an I in the prefix. So like bupivacaine has the I, like the bupi, the I. So that's an amide. The rest are esters.
Yeah, thank you, Dr. Hiral, for that. I think that's it. Go take a break, take a walk, enjoy your evening, guys.
Back, Soja.